You're driving. The car ahead of you taps the brakes. Before you even register why, your foot moves too. A small red light blinked on, and your whole body reacted before your mind caught up. You've done this 10,000 times. But the real answer for why that light is red and not blue or white or purple is far stranger than a simple design choice. It starts inside the wiring of your eyes, and it ends with a railroad accident that never even involved a car. Start with your eyes themselves. You have 3 types of cone cells in your retina, and one of them is tuned to catch long wavelengths of light, the kind your brain reads as red. This isn't an accident of biology. It's ancient. Your ancestors needed to spot ripe fruit against green leaves, and ripe fruit is almost always red or orange. The same cones that once found a ripe fig in a forest canopy are the ones that now catch a brake light 200 feet ahead of you on a highway. Isn't it strange that a system built for fruit ended up steering traffic? In the 1950s, 2 researchers named Leo Hurwicz and Dorothea Jamieson ran a series of experiments that finally proved something scientists had only theorized before. Your visual system doesn't just detect red, it processes it in opposition to green as a paired channel, wired directly into your nervous system. Red and green push against each other in your brain like a seesaw. That means red doesn't just stand out because it's bright, it stands out because your brain is built to treat it as the opposite of safety, of stillness, of green. Red isn't a neutral color to your visual cortex. It never was. There's also a matter of pure physics. Light of different wavelengths behaves differently when it hits fog, rain, dust, or haze in the air. Short wavelengths, the blues and violets, scatter easily. They bounce around in mist and lose direction. Long wavelengths, the reds, punch through. This is the same reason sunsets turn red instead of blue. The sunlight is traveling through more atmosphere, and only the long wavelengths survive the trip in a straight line. A red light on the back of a car behaves the same way. In fog, in rain, in dust, kicked up on a highway, red cuts through when other colors blur into the haze. Your ancestors never drove cars, but the same physics that painted their sunsets orange and red is the physics keeping you from rear-ending someone today. So biology and physics both point toward red. But that's not actually why brake lights are red. Not originally. The real reason goes back further, to railroads and to a mistake that cost lives, before anyone thought to fix it. In the earliest days of railroad signaling, engineers didn't use red for stop at all. They used red for caution. And they left clear, uncolored glass to signal that the track ahead was safe to proceed. A white light meant go. Sounds reasonable until you consider what happens when a red lens breaks or falls out of its housing, or simply wears out after months in the weather. A red signal that loses its lens becomes a white light. A stop signal silently turns into a go signal. Nobody had to make an error. The equipment made the error for them. This is exactly what happened on more than one occasion in the 1800s, when a broken or missing red lens turned a stop signal into what looked like a clear track ahead. Trains that should have halted kept moving. Collisions followed. Investigators traced the failures back to the same design flaw again and again. The problem wasn't human judgment. The problem was a color system where a mechanical failure could silently reverse the meaning of the signal. So railroad engineers rebuilt the entire logic from scratch. Red became stop, and only stop, chosen specifically because it could never be created by an accidental gap or a burned out bulb. Green replaced white for go. Yellow sat in between for caution. This 3-color system, born out of a wiring failure nobody anticipated, is the same basic logic sitting behind every traffic light and every brake light in the world today. Isn't it strange that a light on the back of your car exists because of a problem with train lanterns from over a century ago? Now here's the part that should really surprise you. You'd think red would be the obvious, easy choice for visibility at night, given everything you now know about its physics and its psychology. But your eyes don't actually work the way you'd expect once the sun goes down. There's a well-documented shift in human vision called the Purkinje effect, named after the scientist who first described it in the 1800s. In bright daylight, your eyes are most sensitive to yellow-green light, but in dim, low-light conditions, your sensitivity shifts toward blue and green, and red actually becomes harder for your eyes to detect. In near total darkness, a red light can appear dimmer to you than it really is, while a blue or green light of the same intensity looks brighter. So in the very conditions where a warning light matters most, at dusk, on a dark road, red is not actually the strongest performer for raw detectability. That's the twist. The color your brain treats as danger is, physically, one of the harder colors for your night vision to pick up. So why does it still work? Because detection isn't the only thing happening in your brain. Recognition matters just as much, maybe more. By the time you're old enough to drive, you've seen red mean stop thousands of times. In traffic lights, in warning signs, in brake lights, in emergency exits, your brain doesn't need to work hard to detect the light. It needs almost no effort to understand it. That instant understanding is what actually saves time in an emergency. And time is the entire game when you're driving 60 miles an hour toward the car in front of you. This is where a researcher named John Vygotsky enters the story. In 1974, Vygotsky ran a real-world study, putting a third brake light, mounted high in the rear window, on a fleet of taxis. The idea was simple. Add a red light at eye level, centered above the usual two brake lights on either side of the bumper. His results were dramatic. Cars fitted with the extra centered red brake light were involved in significantly fewer rear-end collisions than cars without it. The study helped convince regulators that a third, high-mounted brake light should become standard equipment. Yes. And within a decade, nearly every car built required one. Look at the back of almost any car today, and you'll see it. Two lights low on the bumper, one centered higher up near the rear window. That third light exists because of one study, one researcher, and one very simple insight. It's not just about the color. It's about how fast your brain can turn a flash of red into a decision to hit the brakes. Put all of this together, and the light behind you starts to look less like an engineering detail and more like a layered inheritance. Your fruit hunting ancestors gave you cone cells tuned to catch red. Physicists explain why that same wavelength survives fog and rain when other colors scatter and vanish. 19th century railroad engineers, reacting to a wiring failure that cost lives, locked red into the specific meaning of stop, a meaning that couldn't be undone by a broken lens or a dead bulb. And in the 20th century, a researcher proved that placing that meaning at eye level, centered in your field of view, could shave critical fractions of a second off your reaction time. None of it was designed as one system. It came together in pieces over more than 100 years, built by people who never met each other and were solving completely different problems. So the next time you're behind the wheel and the car ahead flashes red, and your foot moves before you've consciously decided anything, remember what's actually happening. You're not just seeing a warning light. You're running biology built for spotting fruit, physics built for cutting through fog, a color code born from a train wreck, and a placement decision from a taxi study in the 1970s, all firing together in a fraction of a second, just so you don't hit the car in front of you. It still feels automatic. It still feels invisible. But now you know, it was never simple at all.